So yeah, good afternoon and welcome to the last CSP seminar for the semester. So first, before I introduce the speaker, I do want to thank Shelley Feldkamp, who's the organizer behind the scenes, and also KLA, who's our sponsor, and as well as the two research groups, NCIS and SIPM. So yes, today I'm delighted to have Ambuj Tewari. He is a colleague of ours at the University of Michigan. He's primarily at the statistics department, but he also has a courtesy appointment in the EECS department. So it would, again, I mean, it would have been easy for him to walk over to EC and give a seminar and for all of us to attend, but that unfortunately is not happening at this moment. So in addition to being part of the statistics department and EECS, he's also affiliated with MIDAS, the Michigan Institute for Data Science. He obtained his PhD under the supervision of Peter Bartlett at the University of California at Berkeley. Now about, I would say 8-9 years ago, something in that range, yeah. And oh no, actually even longer than that, because he did a few postdocs, one some at UT Austin and then at TTIC in Chicago, University of Chicago as well. His research interests lie in machine learning, including statistical learning theory, online learning, reinforcement learning, and control theory, as well as network analysis and optimization for machine learning. He collaborates with scientists to seek novel applications of machine learning in mobile health, learning analytics, and computational chemistry. His research has been recognized with paper awards at CORE 2005, CORE 2011, AI Stars 2015. He received an NSF Career Award in 2015, a Sloan Research Fellowship in 2017, and an Adobe Data Science Research Award in 2020. So I leave the floor to you, Ambuj. Please take away.
Thank you, Vijay, for that kind introduction, and thank you also for inviting me to the seminar series. I looked at the other speakers, and you've had a fantastic set of talks, and I hope I'll do justice to the fact that this is the last seminar. I hope it leaves a good taste. Thanks also to everyone who met me in the meetings earlier this day. I had wonderful discussions. Just the keywords on my sheet of notes. It has everything from multi-class classification to social learning, multi-agent reinforcement learning, online dictionary learning, sample complexity bounds for ARX processes, constraint bandits, incentives for privacy. It's a lot for me to absorb, but I think it also shows the tremendous variety of the research topics that you're engaged in. So thanks for taking time to educate me and tell me about your research. Thanks also to my collaborators in this work. I'll be presenting a synthesis of two recent papers, one presented at last year's NeurIPS conference and one at this year's. And jointly, my co-author list includes Jake Abernethy, whom some of you know. I think you know him, you might even know him very well. He was a faculty in the CS department, and he is now in Georgia Tech's computer science department. And then my recently graduated PhD student, Young. He's in Microsoft now. Then my 5th year PhD student, Bakjin. And then my former student, Chansu Lee, whom I co-advised with Jake. He's in Google Brain, Pittsburgh. And finally, last but not the least, Audra McMillan, whom I didn't advise. I didn't have any formal connection with her. She was working with Anna Gilbert in the math department, and she started talking to Jake and Chansu, and then eventually started talking to me about differential privacy and possible connections to online learning. So none of this would have happened without those initial conversations with her. So thanks to all of my collaborators. My talk on one slide, if you don't have time or you sort of get bored and want to leave the talk, that's totally fine. Just pay attention to this, the summary of my talk, and you would have learned something. And then the rest of the talk would be viewed as sort of filling in the details, the technical details. So what is this talk about? The talk is about two models of learning. So there's a classic model of learning called simply statistical learning that typically makes an IID assumption about data, namely that the data that the machine is being trained on is going to be drawn identically and independently from some fixed distribution. And there are two modifications of this basic model. One modification of the basic model is called the online learning model, also sometimes called the adversarial online learning model, which removes the IID assumption. So you want to do an analysis which is probability free in some sense. You want to give guarantees for all sequences that this learning algorithm might encounter. And you also make the learning protocol interactive. So data comes in one by one and you make predictions. So if you add sequential interaction and you remove the IID assumption from the basic IID statistical learning model, you get this online learning model. And on the other hand, you can add the privacy constraint to IID statistical learning, a constraint of the form that if I learn from a given data set, then I shouldn't and if the data set consists of data about individual users, the outcome of my learning algorithm shouldn't convey too much information about exactly who was in the data set, right? So you might add some kind of privacy constraint, which will give you another model of learning where you're still assuming that data is IID, but you want your learning algorithm to be private. And these two models on the surface don't have anything to do with each other. But my point of this talk is that they are fundamentally connected. Not only are they fundamentally connected, in fact, they are connected through an interesting notion of stability. So that's my entire talk on one slide. Two models of learning, both can be seen as variations on the classic IID model of learning, and showing that these two models are connected at a deep level through this property of stability. Okay, so the sort of the technical content of the talk is divided up into 4 sections. The first section gives a very brief overview of the online learning model and the basic results. If you already know something about online learning, please bear with me. Some of this stuff might be just old news for you. Similarly, for those of you who are experts in differential privacy, and I know some of you in the audience are, the section on differential privacy might be sort of too simplistic. So again, please bear with me. Once I get through the first 2 introductory sections and I have laid out sort of what the online learning model means, what the differential private learning model means, then I will get into the actual results in the last 2 sections. The third section, I'll talk about designing online learning algorithms through a differential privacy lens. And I just abbreviate differential privacy to DP on many of my slides. So if I say DP, I mean differentially private or differential privacy. And then I'll conclude with kind of the big result I feel in this area recently that has been proved, very tight equivalence results between the online learning model on the one hand and the private learning model on the other. So that's the goal. Let's get into online learning. Vijay told me that people tend to ask questions at various points in the talk, so feel free to do that. I will by myself, I'll stop at the end of every section to see if there are any questions about that particular subsection of the talk. Okay, so I want to tell you something about online learning as a model of learning. Now, online learning is something that is often used in 2 distinct ways. Sometimes we use online learning just as a way to denote a property of the algorithm. An algorithm is online if it can sequentially process data. So you might, for instance, have an online reinforcement learning algorithm that is interacting with an environment sequentially and getting feedback from the environment. But in today's talk, I will use online learning as something that is denoting not just this sequential interaction, but also a formal model of learning, which is game theoretic in nature and not probabilistic. So this section is introduction to that online learning model. Sometimes it's called adversarial online learning to emphasize that it doesn't rely on probabilistic assumptions. So what's the classic model of learning? Let's say for supervised learning. In supervised learning, we have a bunch of inputs that come from some space script X, and we want to predict some output, which is in some space script Y. And we have classic problems like classification, where my set of predictions has to be in a finite set, 0 through k minus 1, if it's a k-way classification. A special case is k equals 2, which is just binary classification. Or you might have a regression problem where what you're predicting is a real valued quantity, and maybe it lies in some bounded subset of the reals. And the classic assumption in statistical learning is that the learner is given access to a data set of length t. I will use the letter capital T instead of small n, which is usual convention, because in online learning, we're often talking about time. So the total length is capital T. So I'll continue to use capital T throughout, independent of whether the data is drawn IID or not. So you have capital T examples, XY pairs. These are given to the learning algorithm, and its job is to find a good function that can map X to predictions Y. And classic statistical learning makes this IID assumption that each pair here, each XY pair is a draw from some fixed distribution P. It's fixed, maybe not known to the learner, but there's some fixed distribution behind the data generating process. And we assume that there is some class of functions that we want to pick our predictor from. This class of functions could be neural networks of a certain depth, decision trees of a certain depth, maybe just linear functions, but you have some pre-specified class of functions, script f, from which you want to pick a good predictor based on this data. And how do we measure goodness of the functions we learn? Well, we use a loss function. So again, this is very standard stuff. So I'm sure most of you have seen loss functions like the 0-1 loss function in classification, which penalizes the prediction if and only if that prediction is not the correct label. Or in regression, you may have more continuous loss function like the absolute loss or the square of the absolute loss. So that's just very basic notation, essentially, because I think the concepts are probably known to most of you already. And then in statistical learning, our goal for learning is to get a function with low risk. And risk here is just a synonym for expected loss. So the expected loss of a function f on a sample xy drawn from this distribution P is simply what is the expected loss that your predictor incurs when x and y is drawn at random. And you predict f of x, but the true label is y. So that's a number. For each function f, I have a number, its expected loss. And my benchmark, by which I will measure how good I'm learning, will be the best function in the class. So conceptually, if I sort of loop through all of the functions in my class, there's going to be some which has the lowest risk for that given distribution. And that's kind of the best I can do if I'm only predicting within a certain fixed class of functions for that given distribution. Of course, I don't know the identity of f star. If I'm the learner, I have no idea what the true distribution is. I only have samples. So I pick some f hat of t, hat denoting that it depends on the drawn sample. So it's a random function, potentially random function, indexed by t, which is the sample size. And I want to give bounds, guarantees on this excess risk. F star is the best function in the class. F hat is something you picked. Maybe you were very wrong. So this quantity maybe is very large. It will always be non-negative because of the definition of f star, as long as f hat t is also drawn from the same class script f. And statistical learning is about building tools and also building algorithms that can be analyzed using those tools to give bounds on how much data is needed to learn. And typically what happens is that these bounds on the excess risk, they will decrease with t. So the more data you have, the better job you will do of learning. And they also typically increase with some notion of complexity of f. The more complex the function class is, the more you will pay for the statistical price of sort of searching within that function class. So this is very classic statistical learning, has been around for several decades, maybe close to half century. And then sort of the big result in this area, maybe the sort of the fundamental theorem of statistical learning theory is that if we define learnability of a function class as the existence of some learning rule, and maybe this learning rule is computationally intractable, so we don't care about computation here, although there are further models that add an efficient computation requirement on top of the statistical requirement. But here I'm just saying that learnability of a function class simply means that there exists some rule, potentially computationally intractable, whose excess risk goes to zero uniformly over the distribution. So this is sort of classic distribution-free learning. We don't want our rates of convergence to depend on the distribution. I should get the same rate no matter which distribution nature uses to generate the examples. And there's a very clean theorem in this area that says that a class of functions f is learnable. And let's talk about binary classification here, right? So let's assume that f maps every input to either 0 or 1. So it's a class of binary valued functions, and I'm using the 0-1 loss. So I'm just measuring the accuracy of my functions. Well, actually, the error would be the 1 minus the accuracy. So if you look at the loss function, it will be the 0-1 loss. The expected loss under the risk under 0-1 loss will be 1 minus the accuracy of that function. And so a class is learnable in this IID model if and only if the class has finite VC dimension. It's a classic result. And interestingly, a class is learnable if and only if it's learnable through a very simple learning algorithm called empirical risk minimization. And empirical risk minimization is the simplest learning algorithm you can imagine. It simply says that compute the loss on your data set. For any given function, you can see how many errors it's making on the data set you have. pick the one that makes the smallest mistakes or has the smallest loss in general. And that's the function you say, okay, this is the function I pick based on the data. So this is empirical risk minimization. You just minimize the empirical risk, not the true risk under the distribution. And this algorithm will learn a class if it's learnable, and that will happen if and only if the class has finite VC dimension. And I'm not going to tell you what VC dimension is, because that'll take 5-10 minutes. But there is a parameter, a combinatorial parameter, which if it's finite, you can learn the class. If it's infinite, you can't learn the class. So you get this beautiful characterization of learning in this classic model. So what is the online learning model? So in the online learning model, we model learning as an interactive game. So it's a sequential game going on between one entity called nature or adversary, whose job is to generate examples, and then the learner, whose job is to generate predictions. So time runs in discrete steps from 1 to t at any given time, small t. Nature says, okay, I'm going to play this particular example, xt, drawn from the set of inputs. And then learner picks a function. Again, there's a function class, just like there was in statistical learning. And nature then reveals the label. It says, well, here's the true label of this example. And maybe the learner's prediction ft of xt isn't quite right, so they may pay a big loss. Or maybe they get it right, so they don't pay any loss. And this repeats over and over again until t steps are over. Okay, so there are many similarities with standard statistical learning. There is still an input space x. There is still an output space y. There is still a loss function L. And I'm still using functions drawn from a particular class script f to generate my predictions. But the main difference is now this is sequential. So learner can pick ft based on all of the information from previous rounds. And nature can also pick xt and yt based on what has happened in previous rounds. They don't get to see each other's private coin flips. So they can use internal randomization that will not be communicated, but they can see the previous moves. So you note here that in this model, I'm using small xt's and small yt's to emphasize that these are not random variables. I'm not necessarily assuming that nature is just drawing these examples from some IID process. It's not even drawing these examples from any stochastic process, even a non-stationary or a dependent one. So there is, in this model, we do not make any assumptions on how the examples are generated. And nature is allowed to choose future examples adaptively by looking at what has happened on previous rounds. Okay, so this is the online learning protocol. How do we define learnability in this kind of very assumption lean model? Like, I don't have a distribution, so I can't talk about risks. So what is even the goal of learning? And people have thought about different goals of learning. One very common one.
Ambuj,
Yes.
I had a quick question on the.
Yes.
So the assumption is that nature is always going to whatever xt it picks is going to give you the right label.
So there is not even a notion of a right label here. So it could be that yt's are just random 0, 1. Okay. There is a model, there's a submodel of this, which is called the realizable online learning model, where you assume that there is a function f such that yt is always f of xt, and the job of the learner is to just identify which function it is. Mm-hmm. And I'll actually hold that thought because I'll come back to that realizable assumption. But in the most general case, in what is called agnostic online learning, it may be that yt doesn't have any functional relationship to x.
And does nature have a look ahead? As in, does nature know the entire algorithm you're going to produce, or is it only
the nature knows your algorithm as a strategy, but it doesn't know the internal coin flips you're doing? Yes, so
it doesn't know the realization, but it knows the entire strategy.
Yes. So, for instance, if you're doing empirical risk minimization, it may know that that's what you're doing. So that's one of the reasons that deterministic algorithms don't do very well in this model.
Okay.
Yes, both are good questions. Are we assuming any relationship between x and y's? Not necessarily, but sometimes we do. And then the second question is, what is nature allowed to use? So nature can be given, for instance, like the code of the algorithm, but if the algorithm is doing some random flips, they will not be available to nature.
Thanks.
Okay, so how do we define learning in this assumption lean model? One thing we still have is we can compute the cumulative loss of the learning algorithm, right? So we can add up the losses of all the predictions that the algorithm made on all the t rounds, add them up. That's the cumulative loss of my learning algorithm. And then as benchmarks, since we don't have a reference probability distribution, we can simply compute, once this entire protocol is done, all the examples have been revealed, the learner can, in hindsight, compute what would have been the best function just for this particular sequence, right? So if the xt-yt sequence was revealed upfront, which it isn't, in the actual model, it is not revealed upfront. I get to see it one by one. But once it's fully revealed, there is some function in the class that does best on this data set. And again, going back to Vijay's question, are we assuming any relationship between YTs and XTs? Well, that's sort of, you can reframe that question as, are we assuming that this number, this benchmark, is it small? If we assume that this benchmark is 0, for instance, then we're assuming that in hindsight, it will always be clear that there is some function in your class that always predicts the label perfectly. But we don't always make that assumption that this benchmark is 0. If this is 0, we call it the realizable case of online learning.
So Lei has a question.
Yes.
Hey, I have a question. So the benchmark is evaluated based on a single function f.
That's right.
But your cumulative loss is evaluated over a sequence of function, right?
Great question. Yeah. So there seems to be some kind of asymmetry. I'm sort of treating the benchmark a little unfairly because I'm allowing the algorithm to choose the function each time, but I'm not allowing the benchmark to change the function each time. So what's going on?
Yeah, and also the question is the goal here to find a single function? Or
the goal here is to find a strategy for the learner that picks a sequence of functions.
I see. Okay.
Yeah.
So, Ambuj, me in here. So is this definition adding to Lei's question? This is what's, I guess, equivalent of what sometimes we call best single action policies in a bandit problem. If you didn't have functions, if you just had a discrete set of actions, this would be the best fixed action in hindsight. Yes. Okay. Yeah.
Yes, absolutely. In fact, I will have a slide where exactly that will happen.
Okay.
Yes. Okay, so there are two responses to the question of why is there this asymmetry between allowing the function, the algorithm to choose FT, but not the benchmark. First part of the answer is that often in learning theory, we build the first non-trivial model and try to study it. So it turns out that even if the benchmark is weak in the sense that the benchmark only computes the best fixed function in hindsight, that already leads to a fairly non-trivial theory of learning and fairly non-trivial notions of learnability. So that's one response. And maybe that's a theoretician's response. You might say, well, who cares, right? Who cares that you will be able to build some interesting theory? This is not a useful benchmark because maybe if it's truly adversarial, I should allow the best function in hindsight also to change. And that's a fair criticism. And the response to that criticism would be that this type of regret, the best fixed function in hindsight, is just a starting point. Once you understand this regret, then you can start asking, like, what happens if you allow it to change? Unfortunately, you can't allow, in this adversarial model, you can't allow the benchmark to change too many times. So if this minimum over f was a minimum over t length sequences, if I allowed the benchmark also to change the function each time, that definition of regret, it's a perfectly well-defined notion of regret. But unfortunately, in this adversarial model, there cannot exist any algorithm with like a sublinear guarantee on that regret. So that becomes too hard of a benchmark. So there are multiple benchmarks in between this simple benchmark and that impossible to achieve benchmarks that have been studied in the literature. In this talk, I will only work with the best fixed function in hindsight benchmark.
So, Ambuj, could you go back to the sequence that was being followed? Yeah. Oh, okay. So just based on this, nature is picking first. So how does nature pick x1? Is there a...
Nature can pick, and actually you can, the model doesn't significantly change if you ask nature to pick both x and y. The standard exposition is that nature picks x, then you pick predictor, then nature reveals label. But nature can pick, you're only giving more power to nature by allowing it to go first, right? So let it go first.
I guess it knows the algorithm you're going to use, a strategy, so it picks x1 based on the knowledge of the strategy.
Maybe it knows that, it knows that you're going to play this. Okay, I'll give you an example where I feel like you're going to make it.
Right. Hi, may I ask a question? My name is Prakash Narayan. I'm calling from the University of Maryland.
Yeah, please.
The result, therefore, would depend on the xt-yt pair sequence, right? Is there a notion of a worst case sequence? In other words,
Yeah, very, very, very good question. So what are we trying to do? Are we trying to do it like for some sequences? So actually in the full generality, we will say we want guarantees literally for any sequence that might come up. So I will define learnability that a class is online learnable if there is some online learning algorithm such that no matter how nature plays, I can drive my regret, average regret, which is regret divided by the number of times. If I can drive down to 0, no matter what nature does, which sequence actually comes out, then I will say my class is online learnable. So it's actually worst case over all individual sequences.
Okay, good. Thanks.
Now, of course, there are modifications where you might say that, oh, I only want to give guarantees for somehow easy sequence, and you can come up with notions of simplicity of sequences, and that has also been done. But that was a good question because it's a great segue into the fundamental theorem of this particular adversarial model of learning, namely that a class is online learnable in this very sort of worst case sense that you're supposed to drive down your regret, average regret per time to 0, no matter what nature does for all possible individual sequences. Learnability in this sense holds for a function class if and only if the little stone dimension of the function class is finite. So in some sense, the little stone. Was there a question?
This meeting is being recorded.
Sorry, can you please mute? Yeah, go ahead. I don't think there was a question.
Oh, okay. It was just some feedback, I think. Yeah, so a class is learnable in this online learning model if and only if it has finite little stone dimension. And again, I'm not going to tell you what little stone dimension is, although I'll give you a partial characterization in a later section. But the point I want to make is that there is another combinatorial dimension, and it is not the VC dimension, which characterizes learnability in this very worst case adversarial model. And another thing to note is that the third bullet is missing. I'm not saying that a function class is online learnable if and only if it's learnable through empirical risk minimization. Namely, empirical risk minimization, also called follow the leader in online learning, would be an algorithm that at this step of picking a function simply computes the past losses and says, well, this function looks good on the past data. Let me just play it. This algorithm is not in general a good learning algorithm, even though it was a good learning algorithm in the IID model. So ERM or FTL is in general not a good online learning algorithm. And online learning is strictly harder than statistical learning in the sense that the dimension that characterizes learnability in this model is guaranteed to be larger than or equal to the VC dimension. And there are classes where the gap is as wide as you want. So you do pay a price for this very strong assumption-free model. Namely, the number of function classes that are learnable shrinks. Fewer classes are learnable in this more harsh model. Okay? And I said that the connection between the two topics of online learning and differential privacy will be through stability. So I want to just start this discussion on stability on the slide, where just want to give you a little bit flavor of why is it not such a good idea to just look at the past and minimize the loss on the past data. So suppose you do have only two functions, and time again is indexed by the integers, positive integers. The first function gets a little bit of loss, 0.5 on the first round. Second function is perfect, has no loss on the first round. So if you're following the leader or you're doing the analog of empirical risk minimization, at the beginning of day 2, you will say that, well, F2 looks good. It didn't have any loss on day 1. So let me pick F2. And then nature says, I'm going to make F2 look really bad. So I'm going to flip the losses this time around. I'm going to give F2 a loss of 1 and F1 no loss. Then at this beginning of day 3, you will look at the past losses. You'll see F1 has 0.5, F2 has 1. So maybe I should pick F1. And then nature gives F1 a loss of 1 and just keeps flipping like this. So ERM is very unstable. It just keeps fluctuating between these two functions, even though their losses are roughly equal, right? Each function is roughly getting a loss of 1 every other round. So the best function in hindsight here has loss of around t over 2. But the regret of this FTL, you're getting a loss of 1 every round because you're so unlucky. You're flipping back and forth exactly when the losses are flipping. So you're seeing a loss of 1 on every round. So the regret, which is the difference between your loss, which is t, and the loss of the best function in hindsight, which is t over 2, is t over 2, which is linear in t. And so that's by definition not an instance where learning is occurring, because we say that learning occurs in this model if the average regret goes to 0. Here the average regret is half, doesn't go to 0. So FTL is not stable. So how do you make it stable? You can make it stable by being a little bit soft about the past losses. So instead of picking the function with the least loss, maybe we weigh them and we choose them probabilistically. And here's a very classic algorithm in the online learning community. Here, for simplicity, let's assume we only have a finite class of functions. So there are some n functions that you care about. Maybe you can list them out, so it's not a big function class. Initialize their weights to 1. So initially you are agnostic about which function might be good. They all get a weight of 1. And you set some learning rate eta greater than 0. And then at each round, what you do is you pick a function f. You don't pick it deterministically. You pick it with probability proportional to the current weight of that function. So on round 1, you will pick uniformly at random because all weights are 1. But then you will update the weights. And the way the weights are updated is using an exponential update, which is why this algorithm is called exponential weights. You downgrade those functions who are getting high loss, and you downgrade them exponentially. So if a function gets no loss at that round, its weight doesn't change because exponential of eta times 0 is just 1, so the weight remains the same. But if you get a loss of 1, let's say, then your weight will go down by e to the power minus eta. Okay? So you make FTL a little bit soft in this. You make it probabilistic. And so as I said, FTL is just going to pick a function with the least loss, but exponential weights chooses a function proportional to this probability, which is the exponential of eta times the cumulative loss of that function. So it's a soft version of, instead of taking the min, it is taking like a soft min over the previous losses. And so obviously there are two extremes. As eta, this tuning parameter, goes to infinity, you kind of become FTL. You lose your stability. As eta goes to 0, you're very stable because eta equals to 0 means you will not even look at the losses. You will just always be uniform over your functions. So that's very stable. Your distribution never changes. But then you don't do any learning because you're not even not paying any attention to the losses. But if you tune eta properly, you can get a regret of ignoring constants. You can get a regret of square root of t times log n. Okay, so this we would say this is a learning guarantee because the average regret, if I divide this by t, does go to 0. And in fact, it's a very good guarantee because the dependence on the function class size is logarithmic. So you can have many functions and you don't pay a price in terms of a polynomial in the cardinality. You only pay a price which is just logarithmic in the cardinality of the function class. Okay. And one comment I want to make here about the exponential weights algorithm is that it has an interpretation as an algorithm that adds random shocks, random fluctuations to past losses. And the reason I want to highlight this interpretation is because we will see that some differential privacy techniques also add randomness to the input, and I'll start making connections between the whole point of the talk is to start making connections between online learning and differential privacy. So exponential weights algorithm, it turns out, is equivalent to the seemingly different algorithm. What is the seemingly different algorithm? The seemingly different algorithm says, oh, well, FTL had the stability problem. It fluctuates from one expert to the other. Let's just stabilize these algorithms, make it a little probabilistic by just adding a little bit of random shock. So each time I'm about to minimize the loss, how about I add a little bit of randomness to that cumulative loss before I compute the minimum, right? So losses will be perturbed randomly, and maybe that's enough to do well in this adversarial setup. And then I'll have a parameter eta that trades off how much randomness I add. So ZTIs here are some random variables, maybe uniform, maybe Gaussian, right? But I add some random noise. And this family of algorithms has a name in online learning. These are called follow the perturb leader because you're perturbing the losses by a random amount. And it turns out that exponential weights is formally equivalent to a FTPL algorithm where the perturbations are Gumbel. Gumbel is a distribution that shows up in extreme value theory a lot. And actually, one quick way to understand what a Gumbel is, it's like take a uniform, take the natural log of the uniform, you'll get a negative number because uniform random variables are less than 1. So take the log again, but with the minus sign. So log of minus log of u, if u is uniform, is a Gumbel. So if you add Gumbel shocks to past losses, you basically recover exponential weights and you get a beautiful regret guarantee. And we will see that this random perturbation will also be something that happens in DP algorithms. And just kind of almost the final thing I want to say for the online learning model itself is that even though I presented the model in this kind of prediction setting, and this goes back to, I think, Mingyang asked that question of like, is this just the best fixed action in hindsight benchmark? So I'm just making a sort of a clarification with regard to that question, that even though I presented the model in the context of prediction, this exponential weights algorithm actually solves a slightly more general problem, in the sense that all it needs to operate and create these probability distributions are capital N entities that suffer losses. They don't really have to be functions that suffer losses on labeled examples. They just could be your friends who are telling you how to invest in the stock market, and you have N experts, they tell you something. These could be weather forecasters. As long as you have N entities that reveal their advice to you sequentially over time, and you have a way of computing their losses. So at the end of each day, their losses are revealed. Each day you have to pick one of these experts. At the end of the day, losses of all the N experts are revealed, and your goal might be to minimize the regret, namely the total losses you incurred by following different experts at different times versus the loss of the best fixed expert in hindsight. And the same algorithm, exponential weights, solves this slightly more general problem of, it's called the problem of predicting with expert advice in online learning. So here's a summary for the online learning section. IID learnability characterized by VC dimension. ERM plays a big role in statistical learning. Online learning is harder. It's decided not by VC dimension, but Littlestone dimension. I can induce stability by adding random perturbations. In fact, if I add Gumbel perturbations to previous losses, I recover this classic algorithm from online learning called exponential weights. Any questions about the online learning model or this kind of summary of what we know about this model in terms of learning?
Yeah, I have a quick question.
Please.
Yeah, so the function or the learner give to the nature is a randomized function, right? It's not.
That's exactly right. It's a randomized function chosen with a probability distribution that depends on how good that function has been doing on past losses. Yes.
But it's not a realization with that probability. It's kind of.
So you get a distribution of a function and you just pick one function by drawing from that distribution, and you say that's the predictor at that point.
And that function is given to the nature?
Yeah, you use that function. So on that example, you will say, okay, I commit to this function to predict the label of this particular example.
Yeah, so so then the function becomes deterministic after you pick that.
After you pick that, it does, yes.
Yeah.
So my random flips in drawing this distribution, these flips are not available to nature.
Oh, okay, okay. So the nature will not see
my
that function
flips.
you picked. Okay, okay. Got you. Thank you.
Any other questions? Okay, so I'll move on to differential privacy, and hopefully this will be quicker because I don't have to, some of you already know about the basics of DP. So what is DP? So differential privacy comes from a desire to preserve sort of a privacy of individuals whose data lives as part of the data sets that we train our machine learning algorithms on. But for this talk, you can sort of think of it as a stability property. So differential privacy is the property of an algorithm, often called a mechanism in this literature. You assume that your algorithm is some kind of a randomized algorithm that looks at a data set, script D. And what you say is that this algorithm better be stable when I just change one example in my data set. What does that mean? If D prime is another data set that mostly agrees with D, but just disagrees in one example, right? So you have a data set of 1 million examples. You have another data set. All the examples are the same except maybe the 500th example, right? So these are two data sets that are one apart. And in that case, the distributions, the output distribution of the algorithm should be close when it runs on the first data set and it runs on the second data set. In particular, for any set B in the range of the algorithm, the probability of the first algorithm outputting something in that set, that probability shouldn't change by more than a multiplicative factor of e to the epsilon, where epsilon here is a parameter. The smaller the epsilon is, the more you're demanding privacy. Epsilon is very large, you're not demanding very much privacy. This is called pure differential privacy. And a classic mechanism is the so-called Laplace mechanism. And again, I won't go into the details. The point I want to make here is that one of the classic mechanisms of differential privacy adds a carefully chosen random variable to preserve privacy as a perturbation. So this is very similar to how we saw that Gumbel perturbations were being added to the losses to compute the next distribution over functions in online learning. So we add, if your function has a low sensitivity, and again, we don't have to get into the details of what sensitivity means, the definition is on the slide. But the point is that if you want to compute a function, but you want to be private, you can add Laplace noise to the function before releasing its value, and then you will have this pure differential privacy, where the variance of the Laplace has to be chosen with knowledge of the desired epsilon. There's also a Gaussian mechanism, again, for functions with low sensitivity, meaning the function itself doesn't change too much, has some kind of a Lipschitz property. When you make a single change to its input, you can add Gaussian perturbation, and that satisfies a modified version of privacy where you allow for an additive error. So in pure differential privacy, there is no additive error, it's just multiplicative, which means that if this probability is 0, the left-hand side probability also has to be 0, right? Because you're not allowing any additive error. So in the Gaussian mechanism, what happens is that you don't get pure privacy, you get something called approximate privacy. So the probability of the algorithm outputting something in a set B when run on D is close to what it does when it's run on D prime, but now the closeness is there's also an additive factor of epsilon. And now there are two parameters in your privacy definition, epsilon and delta. Thankfully, the dependence on delta is often very, very mild. Like here, you can see that the variance of the Gaussian that you need to add to get epsilon delta privacy, it depends logarithmically on 1 over delta. So you can often make delta very, very small. So a little bit of, you can say that this additive error is extremely small, okay? So now you can add this privacy constraint on top of learning algorithms. So you can still remain within the IID learning framework. So you can say, okay, just classic IID learning, I don't care about this online learning. Maybe this worst case analysis is too harsh, who cares? I just want to do my standard probabilistic assumptions, data is nice and non-adversarial, but I want my algorithm to be private, right? Because I do care about preserving privacy of the people whose data went into the dataset. So now what's interesting is that again, ERM no longer works. So it doesn't work to perform empirical risk minimization because that's a deterministic algorithm. It will not satisfy privacy. So again, privacy researchers have argued that we need to make empirical risk minimization more stable. And interestingly, the way they make it more stable is exactly this exponential mechanism. So they say, instead of picking the function with the lowest loss in the data set, why don't we randomize? Why don't we pick a function with a probability proportional to e to the power, and now it's minus epsilon. So this epsilon is the privacy parameter you want. And if you pick a function with this probability distribution, this is now a randomized algorithm, and data set goes into this learning algorithm, and a randomized function, a random function comes out, and this algorithm viewed as a mechanism operating on the data set will be epsilon pure differentially private. And this was a seminal paper in 2011 that started this investigation of what can be learned privately. If we insist on privacy, what can be learned? So they showed that finite classes, a function class consisting of only n functions, maybe n is very large, but it's finite, that can always be learned using this exponential mechanism. All you pay is that the sample complexity becomes a little bit higher. So if you don't want privacy, sample complexity of learning a class of functions with n functions in it, if you want to achieve alpha excess risk and with high probability, with probability, I should say at least 1 minus beta. This is not, shouldn't have been beta, this should have been 1 minus beta. I want to succeed with high probability. Then the sample complexity scales like log n plus log of 1 over beta divided by alpha square. If you make it private by having this exponential mechanism, then you can still learn the class with essentially the same sample complexity, but it goes up a little bit. So if the privacy requirement epsilon is less than the access risk that you demand, then there is a factor of alpha over epsilon that you have to pay more. So yes, you can still be private, but you need more samples. And this is a classic trade-off. Like privacy often doesn't come for free. You have to sacrifice something else. Here, that something else is you're sacrificing the sample complexity. So summary of the differential privacy part. Finite classes can be learned even under the privacy constraint, but the price is higher sample complexity. For infinite function classes, I told you that without the privacy constraint, you can learn them even if they're infinite, as long as they have finite VC dimension. Does the same hold for under privacy? Is it still true that I can learn classes in a private way that have finite VC dimension, and maybe the only price I'll pay is an extra sample complexity, and that's fine. That doesn't happen. So the rest of the talk, in the next 10-15 minutes, I'll tell you that that does not happen. VC dimension does not characterize learnability under privacy constraint. In fact, little stone dimension characterizes it, which is the dimension coming from online learning. And already some evidence has started to occur in this talk that online learning and differential privacy somehow look similar, because exponential mechanisms are central to both, random perturbations are central to both, empirical risk minimization is not a good idea in both, and stability to single perturbations of your data is central. It's central to the definition of differential privacy, and also in the online learning model, data comes one by one. So you don't want your algorithm to suddenly do something different if the nature just reveals one more example. So that's kind of the reason why, well, it's not exactly the reason, but that gives you reasons to suspect that maybe VC dimension is not the right thing if you add the privacy guarantee on top of, even if data is IID, learnability will be characterized by a different dimension. It so happens that it's the little stone dimension. Any questions on the differential privacy part?
There aren't any questions, so maybe you can proceed.
Okay. So in the interest of time, what I'll do is I'll skip over the third section and I'll directly jump to equivalence results, which anyways, I think that's the big news are these equivalence results. And then I will finish with what we added to these equivalence results that are already new, what we did beyond them in our NeurIPS paper. And there's one kind of open problem which will be good to settle. So what have we just discussed? You can learn even infinite classes of functions in the IID setting if they have finite VC dimension. In fact, you can learn them using just a simple algorithm called empirical risk minimization. And we've asked this question, what is the dimension that will characterize learnability when I add this privacy constraint, even if data is IID? Will it continue to be the VC dimension like in classic learning theory, or will it be a different dimension? So early on, well, not early on, like actually a few years ago, people started having this suspicion that even the simple function class of threshold functions, so your data lies in a one-dimensional real line, and your functions are simply threshold functions. They say 1 if x is less than some threshold, and they say 0 if x is larger than that, right? So it's a step down step function. And this is a very simple class. Its VC dimension is 1 independent of how many thresholds you have. So maybe you put thresholds at n locations on the real line. That's a function class of size n. Its VC dimension is 1 independent of n. And there was a result. It was built up on several papers, but culmination happened in this Noga and co-authors paper in 2019, where they showed that if you want to learn these thresholds, n thresholds, privately, where your notion is approximate DP, you will need log star n examples. Now, log star n is a function that grows really, really slowly. Log star n is a function that asks how many repeated logs do you have to stay before you get an answer less than 1. So for all practical purposes, it's less than 4. But it's a function which is going to infinity. So theoretically, it separates classes that can be learned privately from classes that can be learned non-privately, because VC dimension of this class is 1. So it can certainly be learned non-privately, no matter what n is, but the number of samples here grows with n. So if you consider all thresholds on the real line, that class is unfortunately not learnable when you add this privacy requirement. And interestingly, And here's where the connection with online learning becomes even more interesting. This little stone dimension that, again, I haven't told you what it is, but it has this very interesting property that was also proved in this. This was a landmark paper, Nogalon 2019. They also showed that the only way a function can have high little stone dimension is if these thresholds are hiding in that class. What does that mean? Here's the formal statement. What they showed is that any class which has a high little stone dimension, let's say the little stone dimension is D, it must contain log D thresholds. Containing log D thresholds means that there are some m functions in your class and m data points x1 through xm, such that you get this step down behavior. So the first function is 1 on the first point, 0 on others. The second function is 1 on first 2 points, 0 on others. The third function is 1 on the first 3 points, 0 on others, and so on and so forth. So you have a bunch of threshold functions hiding in your function class. So if you have high little stone dimension, you must have lots of thresholds hiding in your function class. So your function class must be really hard to learn privately, because thresholds are hard to learn privately. Okay, so imagine, so very immediate implication of that word is, if a function class is privately learnable, in this ID setting where we demand privacy, it must be online learnable. And the proof is through contradiction. Assume it's not online learnable, its little stone dimension must be finite, so there must be lots of thresholds hiding in the class. Thresholds are hard to learn privately, so the class cannot be learned privately. Okay, so amazing result just from 1 year ago. So this shows that private learning implies online learning, but it's a non-constructive proof. So we don't have constructive reductions that will take an approximate DP learner and somehow convert it into an online learner. This is a proof by contradiction. But nevertheless, it establishes a connection in one way. And the big result this year, earlier this year, this was a best paper award at Fox, Foundations of Computer Science, which is one of the top conferences in theoretical computer science. Mark Bunn and co-authors showed the other way around. So they showed that if a class is online learnable, then it is also learnable in this approximate differential privacy model. And interestingly, this proof relies on a property they call global stability. So again, stability is the key. And remember, the whole point of this talk is to say that online learning and differential and learning classic learnability under privacy constraint, these two are related. And the reason they are related is stability. So it's really nice that this paper also fundamentally relies on a stability property. And global stability is actually even simpler to understand than differential privacy. Global stability of a learning algorithm is simply the requirement that there must be whatever function P is generating your data. So remember that in the private model, I'm not being worst case. I'm still allowing nature to just be very benign. It's just choosing randomness. It's just choosing examples from a distribution. But I am insisting on privacy. So this global stability requirement is simply the requirement that for every distribution P, there must be some function which has some small probability of always being in your output. Okay, so we say that a learning algorithm is eta T globally stable if for any sample of size T drawn from this distribution, there is a function F which can depend on this distribution, which is output by my randomized algorithm with some constant probability, like some lower bound. The probability of outputting this function F is at least eta. And this is trivial. You know, if I have a finite function class, simple averaging argument will show you that, well, there has to be some function with probability at least 1 over the size of the class, right? Because it cannot be that all functions have probability less than 1 over n, because the probabilities have to add up to 1. Interestingly, what they showed is that this argument, which is trivial in the finite case, actually extends to the infinite case, provided the function class has finite little stone dimension. So if the function class has finite little stone dimension, remember, which is if and only if it is online learnable, then they can create a globally stable learner. And then furthermore, they can convert a globally stable learner into an approximate DP learner, which finishes the other direction. So Alon et al. Came along and said, hey, look, private learnability implies online learnability. And these guys came along and said, online learnability also implies private learnability, because if it's online learnable, I can guarantee global stability, and global stability can be converted into an approximate DP algorithm. So that that was a big result, connecting the two models. And what we did in our NeurIPS paper, and I don't have time to go into the details, the paper is linked at the end of the talk. What we did was we extended this characterization, which so far had only been shown for binary classification. So we made two contributions. One, we showed that this continues to hold for multi-class. So for multi-class classification, where you have more than two classes, the definitions of learnability change. There are other combinatorial dimensions that characterize IID learnability and online learnability. But nevertheless, this equivalence stays intact. So a class of functions in the multi-class setting is learnable under the 0-1 loss if and only if it's online learnable, if and only if it's privately learnable. So it's really nice that in some sense this result is robust. It doesn't matter whether you're talking about binary classification or multi-class classification. So we expected the result to also hold for regression, the case where you output real valued predictions. And interestingly enough, the current proof techniques fail in one direction of the proof. So we are able to show that even for regression, meaning namely real valued function classes, approximate DP learnability does imply online learnability. So that direction continues to hold. But online learnability implying approximate DP is an open problem. And I think it's a very fascinating open problem because I talked to Mark Bunn, one of the authors of the Fox Best paper this year, and he said that, yes, it does seem like the current techniques don't quite let the current proofs go through. So in other words, it's not just we failing to establish the results using the current techniques. I think there might be something in the current techniques inherently that don't. So either we need new techniques, or it could actually be the case that regression behaves very differently for privacy and you don't have the equivalence. And either way, it will be very interesting to settle the regression case. Okay, so I can conclude the overall talk by, again, reminding you of the central message of the talk. There are two models of learning: online learning, an interactive model of learning that doesn't make any probabilistic assumption. And then there is a private model of learning that does make the ID assumption, but insists on the requirement of privacy. These two models on the surface don't seem to each other. After all, one is assuming probabilistic mechanism and the other is not, but they are fundamentally connected through a particular type of stability, namely stability in the output of your algorithm to one example changes of your data set. It's a crucial property in both models. And it's remarkable that you can show formal equivalence results, which we now know for binary classification and multi-class classification, that a class is online learnable if and only if it's privately learnable. For regression, we only have it one way, and it remains an open problem whether we have the implication in the other direction. Thanks.
So let's do one thing. Let's actually have the discussions go, and then we can sort of open up for broader questions. So Sheru, do you want to go first? Yeah, I think Ambuj, you may have to stop sharing before they can pick up.
Yeah, sure, I can go first. Let me share my screen. Can you see my screen? Okay.
Yes, I can see it.
Yeah, cool. So first, I would mainly discuss about the equivalence result part, and I will skip the summary. And I have a couple of questions I would like to ask. The first is that in the paper, it shows, in order to show the equivalence between the private learnability and the online learnability, it needs to show, first to show that the private learnability will imply the online learnabilities. And in the paper, it gives us the lower bound of the sample complexity to privately learn the threshold. And
yes.
This result only holds for the special case when the differential privacy, the privacy parameter of the differentially private algorithm, when the epsilon equals to 0.1.
Right.
So I was wondering, can those results, how about for the other private algorithms, for the other privacy parameters?
Oh, I see. Yeah. So when we say you want to be you want to privately learn a class, what we typically say is that the sample complexity should be finite, no matter what. There are 4 parameters. I mean, it's hard to keep track of all the parameters, right? There are 2 parameters coming just from normal learning, right? There's an accuracy parameter, and then there is a parameter that quantifies what is the probability with which your claim will fail. So that these are called pack style bounds. There's an epsilon and a delta, which unfortunately also are used in DP. So when you have DP, you have to have alpha, beta, epsilon, delta. So the definition of learnability is that the sample complexity should be finite for all values, right?
Yes. Yes.
So in order to show a lower bound, it suffices to pick one particular value for which it's not finite. But your question is still well motivated, right? Because maybe you say that, well, maybe I don't want to learn with 0.1. I'm happy with the higher value of epsilon, right?
Yes, yes.
I don't have an actual answer for you. My suspicion is that unless you make epsilon really, really big, like as big as you basically are not insisting on any useful privacy, I feel like the lower bound should continue to apply.
Oh, okay. Yeah, okay, thank you.
It's a good question, because maybe there is a spot between at 0.1 and the spot where it becomes uninteresting, where maybe a phase transition happens. I don't know.
Okay, yeah, thank you. And for my second questions, I was wondering, when we built this differentially private learner from the globally stable learner, yes, we have you are using 2 steps. First, you use the stable histogram algorithms to select the sublist. That's right. From the long list. And then you apply the exponential mechanism to select the hypothesis privately. Right. So my first question is that, is the first step necessary? That why we need to first choose the sublist first? Why we cannot just apply the exponential mechanism directly to select that hypothesis?
Yeah, that's a very good question. So in fact, it's the other way around. So stable histogram is the necessary part here. You don't have to run the exponential mechanism afterwards. The only reason they do it is that you get a slightly smaller sample complexity if you further run exponential. The stable histogram is the part of the proof where privacy is introduced for the first time. So all of the processing before, now again, I'm getting into the details, so this discussion is probably not going to be very meaningful to the rest of the audience. But the way the proof works is you run some online learning algorithm multiple times, whose output you use to create this meta algorithm, which has this global stability property. And then you run this globally stable algorithm many, many times, and that goes into the stable histogram algorithm, whose output is given to an exponential mechanism. So the question that Shura is asking is like, is it necessary to have the stable histogram? Can we just directly go to exponential mechanism? I don't think so. I think stable histogram is the piece that makes this pipeline private. Everything prior to stable histogram is not private. And just running exponential mechanism on the output of a non-private, you're not going to magically get privacy out of it.
I see. So suppose that we keep both the stable histogram algorithm and the exponential mechanism. So why when we choose the shortlist, we need to guarantee its privacy? I mean, because the exponential mechanism already guarantees the differential privacy.
So the sublist is the stable histogram. The idea of the sublist is that because your function is your algorithm is globally stable, there is some function which is appearing with some constant probability in the output, right? So so there is this intuition in differential privacy that that when you create like global summaries of your data set, like a histogram, you add some randomness, right? So it's often very hard to preserve counts of underrepresented bins. And this is a problem in real life. Like a lot of people don't like the fact that the US Census is using differential privacy, because some researchers are interested in studying small groups. Like maybe there are only, I don't know, 25,000 such people in the US, right? What happens is that their counts are changed more to preserve differential privacy. Because if you could get that count, like that's a small minority group, right? So you might be able to pinpoint who is there if you didn't add enough noise. So the stable histogram, what it says is that if there is some function which is occurring with some constant probability, then I can guarantee it will still be in my list after the stable histogram. So the whole point is to insert some privacy preserving, not privacy preserving, a privacy inducing computation while at the same time retaining a good function, because exponential mechanism is only going to do as well as the functions you retain, right?
Mm.
So if the function retained is bad, like if you threw out a good function, then it doesn't help to run exponential mechanism on that.
I
So
see.
that's the beautiful property of stable histograms, that the globally stable algorithm is guaranteeing that, hey, there is one good function which is occurring, maybe it's a very minuscule, actually in the paper, it's exponentially small in Littlestone dimension. So the good function only occurs with e to the power minus d probability, but it's constant as a function of sample size. It's small, but it's constant. And it will be preserved after stable histogram, because stable histogram is going to add noise. It's going to maybe drive down small counts to 0. You may not see it, but this function, which has some constant probability before going into it, it will still be preserved. So you will not throw out all the good functions.
I see. I see. Yeah, thank you. I think, yeah, that's answer my question. So I think I'm done with my question. I think I can leave the time for the scene.
Sure.
Do you want
Thank
to?
you.
Yeah.
Thank you. Yeah, those were all great questions. It
Shane,
looks
yeah.
like you really got into the details.
Yeah. Oh, can you see my screen?
Yes.
Yeah. Let me just jump right into my question. So basically, we are like checking the online learning from the DP perspective. So my major question is will the online learning be constrained by the DP? For example, like we have a very strong assumptions imposed by the DP, like the rank 1 restriction. And in the DP algorithms, we have to solve this problem, optimization problem each time. And instead of doing some like a gradient-based update. And the last one is that we may have like some loose bound like returned by the DP side. So for example, in the follow the probability algorithms, the bound may depend on the dimension of the action set. So that's my major question. Yeah.
But that's a great question, and I think it's a very valid point. So first of all, I should clarify to others that this question is about the third part of the talk that I had to skip due to time. At a high level, that part of the talk is, the message is, you can use the DP lens, you can use DP primitives to design online learning algorithms, and the fact that your primitives are DP kind of give you regret bounds. We have a lemma that says that if you use DP primitives to build your algorithms in an online learning framework, you will get online learning bounds. Yeah, so that's the highlighted third bullet point. But what the comment here is that maybe you're paying a price. Maybe by constraining your primitives to be DP, you're getting hit by some price which you otherwise have not paid had you just designed the algorithm from scratch. So my answer is it depends. So yes, you are right that in certain situations you pick up either assumptions you don't want to make, for instance, a rank 1 assumption which you need because a certain DP primitive I was using had to have that assumption, so I just borrowed it. So in some cases you might inherit a bad assumption, or maybe your algorithm is not as efficient because the DP primitive you're using is not as efficient. Or you might get a bound which is looser because maybe the DP guarantee has extra dimension factor and you inherit it in your online learning. All of those bad things can happen. Yes, I agree. But on the other hand, we also had instances in the paper for the experts problem and for the bandit version of the same problem. We got near optimal results.
Oh, cool.
So it doesn't always happen. And I would say it's an ongoing research topic to understand if we can always avoid paying the price. Like maybe the price we're paying here is just we are not being smart enough about using the right DP tools. It's not clear to me that there is inherently a price in designing online learning algorithms through DP primitives. Yeah, so I would say that you don't always pay the price, and we don't currently know if it's inevitable. Like, are there situations where you can show that any kind of conversion of a DP algorithm into an online algorithm will necessarily give you suboptimal results. I don't know of such a strong lower bound.
Okay. Okay.
Does that answer your question?
Yeah. Okay.
This is a great question, and again, I feel like you really took the effort to understand the paper, because you can't ask these questions based on a superficial understanding. So thanks.
Yeah. Okay. Thank you.
So Sheru and Shin, thanks a lot. So I think there are a few more questions. I think if I know, Clay has his hand up. I had a question, but I'll let Clay ask first. Yeah. Go ahead, Clay.
Okay, thanks, Ambuj, for a very interesting talk. I'm curious, how critical are exponential weights? Like, in your follow the perturbed leader, what if you used a different distribution besides the Gumbel? Would that be equivalent to some other notion of privacy that maybe was a little weaker than the usual differential privacy or something like that?
Great question. So why Gumbel? Yeah, so Gumbel is related to exponential weights, which is kind of related to epsilon pure dp. What if we play around with the distributions? Maybe we get other notions. That does happen. So the part that I skipped over, the third part, that's the New Rips paper from last year. We actually give a stability condition, which is inspired. Actually, let me pull up the slides. It will be easier to just show you the slides, because I think you asked a question that I had the answer to, but I skipped that part. So let me quickly go. So online learning. Yeah, so we define a stability condition for online learning using a divergence. So this divergence measures how much the distribution is changing when one loss vector gets added to the online learning algorithm. And this is a very general definition. You can choose any divergence of your choice. If you choose it to be the max divergence, you get this very precise connection to differential privacy. But as you said, if you only care about designing online learning algorithms, you don't necessarily care about privacy. You may want to be more general in imposing stability. Maybe you want to use different divergences, and we do use divergences other than the max divergence for some of our online learning settings. So that freedom is in fact useful. To the other part of your question, like other randomness, it turns out that for a lot of standard like scalar random variables that we teach in probability 101, like gamma, Frechet, Pareto, it turns out that all of them, even though the actual algorithm is not exponential weights, that exact equivalence is only for Gumbel. If you look at the final regret bound, it seems like a lot of distribution lead to the final regret bound, which is the same, and it's actually optimal for this problem. So it appears that there's a lot of freedom in choosing. The randomness Gumbel is not special. It's only special to the extent that it gives you an exact equivalence with exponential weights.
And so here, this differentially stable, that is what is
For
used?
all of these, it is the standard DP divergence. Yes.
I see. Okay. So you don't. Okay, that makes sense. All right. Thank you.
Yep. Yeah, that was a great question. Thanks.
So Ambuj, I had a question, was more if you have this equivalence between online learning and DP, so DP has a lot of other sort of results like the composition theorem and various things.
Yes.
So what is the equivalent of that in online learning? Or is that not a meaningful question?
Yeah, I'm trying to see what will be the meaning of that question. So composition in DP means I have two mechanisms, I'll compose them, and the guarantee would be in some systematic way related to the guarantees of the components.
Yeah.
Online learning algorithms, I'll have to first think about a composition operator for online learning algorithms.
Yeah. Is it the same as just saying I take my interval t and I subdivide it? And is that not the right way of thinking about it? Or maybe that's...
I subdivide, I run one algorithm on the pieces, that generates some intermediate values, and maybe there's a higher level algorithm that looks at that.
Yeah.
So might compose algorithms in that. Yeah. I mean, I think, I don't know. I mean, I haven't even thought about the composition operator, leave alone give you some kind of equivalence. But I think it's a very interesting question. Yeah. What about, so this is just talking about equivalence, like, oh, the class is privately learnable if and only if it's online learnable. But what about properties of privacy? Like, for instance, composition. if I think if there is an interesting notion of composing online learning algorithms, then the question will be interesting. Yeah, I don't know of any sort of standard composition of online learning algorithms, but I can see like the one you described maybe is an interesting one.
Yeah, anyway, that was just a question along those lines as to where do you see, how far do you see this equivalence going?
So I actually, what I feel as the logical next steps would not even go as far as like these abstract properties like composition and post-processing, right? There's also a property called post-processing. Like if I do some more processing on top of something which is private, it remains private, right? So maybe you can say, oh, I run an online learning algorithm and I do some more processing, right? Is there a version of post-processing for online learning? So you can ask those questions, but I think the more immediate questions are, as I said, one of the directions is very, very non-constructive. It's a proof by contradiction. I generally don't like proofs by contradiction. Like I want like a really tangible reason why private learnability implies online learnability. Like I want to see an algorithm, right? You give me a private learning algorithm and I want to compose that algorithm with other primitives to build an online learning algorithm and do a regret analysis solely relying on the property that the primitive I used was DP, which would be another way to prove the known implication from private to online learning. So I feel like algorithmic reductions, especially efficient reduction, in which case you call the black box you're using only a polynomial number of times. I think these reductions are probably very, very important. And also understanding to what degree this equivalence holds. Does it only hold for discrete problems like multiclass and binary, or does it hold very generally when the thing you're predicting is, as I mentioned, the regression case is open. So I feel like immediate for short term, that's probably would be very interesting to settle. But I think on a longer term, you could ask questions about these more abstract properties. Is there equivalence at the level of these abstract properties also? There, I won't even hazard a guess because I don't know what is even the right formulation of the question.
Are there any other questions from anyone else? Sorry, yeah, I know the seminar has gone long.
I know we went.
A lot of good questions, but actually, Clay has a question. Yeah, please go ahead, Clay.
Yeah, just one last question. In this result you mentioned at the end, your extension of the multi-class case, is there a notion of dimension there that characterizes?
Yes, yeah. I didn't have time. There is definitely on the statistical learning side. Actually, in our meeting, it already came up. On the IDs, multi-class learnability, Natarajan dimension is the right notion. And for the online learnability, Danieli and Shalev-Schwarz defined it. They just called it multi-class Littlestone, but I think people will start calling it Danieli Shalev-Schwarz dimension. Okay. But there is a notion of online learnability also for multi-class. It doesn't currently have a name, but whatever that dimension is, it happens to be the same that also characterizes private learnability through our equivalence result. And I can send you a reference for the paper that defined the dimension for online multi-class.
Okay. Yeah. Thank you very much.
And the connection with thresholds remains intact. So it's really nice parallel. So there's a notion of thresholds you can build for multi-class predictors also. And the way you prove the result is exactly by showing that if your class had a high dimension, it must be hiding thresholds and so on and so forth.
Okay.
Any more questions? Well, if not, let's thank Ambuj for a stimulating talk.
Yeah, thank you all for listening and thanks for your patience and running like we're full 20 minutes over.
Oh, actually, Sue, someone raised their hand. Sue, you had a hand raised. Do you want to ask your question or? Oh, yeah. Oh no, it's just clapping. Sorry.
Oh, right. Okay, that's fine.
Yeah. All right. Thanks a lot,
thank
Ambuj.
you all. Thank you all for coming. Really appreciate it.
And thanks everyone for staying there. Thanks. Bye.